Swayam Prabha. Digital India. Educated India.
Welcome to this fourth lecture of week 12 or module 12 of this NPTEL online certification course of environmental soil chemistry. And in this week we are talking about different analytical methods for assessing soil pollution. And in the previous three lectures we have talked about different types of instruments or methods which we use for analysis of different inorganic pollutants in the soil. We started with nitrogen and we also talked about phosphorus. So in today's lecture we will be talking about basically salts, then we will be talking about trace elements and other elements, total elemental analysis, and then we will be moving towards the organic pollutants. So, let us start today with the analytical methods for salts in the soil. Now, you know that accumulation of soluble salts in soil profile obstructs crop growth by increasing the osmotic potential of the soil solution and inducing specific ion toxicities of nutrient imbalance. So, the salty soils are, the soils which are higher which shows high salinity are not suitable for plant growth. And there are several salts which are mainly responsible for salinity, but the principal cations are basically sodium and then calcium and also magnesium. And as far as the principal anions are concerned, the principal anions are mainly sulfates and chlorides. Apart from that, some minor amounts of potassium, bicarbonates, carbonates and nitrates ion also may be present. Now, high concentration of sodium at cation action site disperse the solids and impedes water and air movement, and as a result of that there is a crust formation at the soil surface. And the sodium saturated soils are not physically beneficial for the growth of the crop. That is why we generally go for different types of treatment to reclaim the soil salinity. So, high concentration of sodium at cation action sites always is harmful as far as the soil physiochemical properties are concerned. Now, there are mainly two methods which we use for measurement of salt concentration in the soil. One is through electrical conductivity meter or EC meter, and the second process or second method is electromagnetic induction method. So, we are going to discuss both of them. So, let us start with the EC meter or electrical conductivity meter. Now, this EC meter is an instrument which basically measures the electrical conductivity in a solution. Now, this electrical conductivity depends on several factors. The first factor is concentration of ion. Obviously, this higher concentration of the ion obviously goes with the higher electrical conductivity. Since each ion has its own specific ability to conduct current, electrical conductivity is only an estimate of the total ion concentration. Now, you might ask me why we go for the electrical conductance measurement while we measure the salt concentration. Now, salt are basically composed of different types of cations and anions, and these cations and anions are known for conducting the current. So, that is why while measuring the electrical conductivity, then we can have an idea about the salt concentration. So, concentration of ions, as I have mentioned, that each ion has its own specific ability to conduct current. Electrical conductivity is only the estimate of total ion concentration. Now, the second important factor is the temperature of the solution. Remember that higher the temperature, higher the electrical conductivity. Now, the conductivity of a solution is highly temperature dependent, remember. Therefore, it is important to either use a temperature compensant instrument which can automatically calculate the temperature compensation or the changes in temperature, and based on that it can compensate the reading, or calibrate the instrument at the same temperature at the solution being measured. So, there are several ways to take care of this temperature variation. The third important factor is the specific nature of the ions. That means specific ability, higher the specific ability and higher valency, higher will be electrical conductivity. So, you can see that electrical conductivity depends on several factors. Now, this EC meter, the basic principle of this EC meter, as you can see, this is an EC meter. So, there is an electrode, and in this EC meter basically the principle says that the two plates are placed in a sample and a potential is applied across the plates, which is basically normally a sine wave voltage, and the current is resulting current is being measured. So, electrical conductivity is denoted generally denoted by the symbol sigma, and its SI unit is Siemens per meter. Generally we it is called Siemens per meter, okay, or sometime we call it deci Siemens per meter also. So, Siemens per meter or deci Siemens per meter is their SI unit. Now, reverse of electrical conductivity is known as the electrical resistivity. Remember, the reverse of conductivity is resistivity, which is denoted by a symbol rho, that is this symbol, rho symbol. And remember that there is a relationship between the potential, that is we denote the potential by V and current by I. So, there is a relationship between the potential V and current I, which is given by the Ohm's law. Now, according to Ohm's law, the current increases with the increase in potential. So, you can see the current increase with the increase in potential means the current is proportionate to the voltage. I am sorry, the current is proportional to the potential V. So, V varies as I. So, you can write V equal to R I, where this R is a proportional constant, we call it a resistant. So, or in other words R equal to V by I. So, resistance also depends on the temperature, and increase in temperature decreases the resistance. So, that is why there is a profound influence of temperature in measuring the electrical conductivity, and this is how we measure the electrical conductivity in the lab. Generally in the lab we use the electrical conductivity meter to measure the conductivity of the soil water solution, and we can prepare the soil water solution in different we can measure the electrical conductivity in different ways. We can either make a soil water solution with a fixed ratio of 1:2, or we can make a saturated paste. Saturated paste means we saturate the soil with the water and keep it overnight, and the next day we measure the electrical conductivity of that paste, directly inserting the electrode into that into that paste. Another way is to extract the saturation extract. Saturation extract basically is done from by the help of a vacuum pump as well as Wagner funnel, and the saturation extract also by extracting the solution or saturation extract, we can also measure the electrical conductivity. So, there are different ways of measurement of electrical conductivity. However, we all measure them using this electrical conductivity meter. So, let us move ahead and see the next important thing, that is electromagnetic induction. Now, the electromagnetic induction was discovered by Michael Faraday in 1831, and James Clerk Maxwell he mathematically described it as a Faraday's law of induction. So, the exact law says that the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. So, in simplified form, this could be achieved by when a conductor is placed in a moving magnetic field. So, this situation can arise when we place a conductor in a moving magnetic field, when for example, when using AC power source, or when a conductor is constantly moving in a stationary magnetic field. So, there are two ways which through which we can realize this Faraday's law of electromagnetic induction. So, let us see in the next slide. So, in the next slide, for example, in this picture you can see that this electromagnetic induction can be achieved when a magnet. So, suppose this is a magnet. So, this magnet and a wire. So, using this magnet and wire we can create the electromagnetic induction. How? So, when a magnet and a wire move relative to each other, a voltage is induced according to this Faraday's law of electromagnetic induction. So, when we move these two with relative to each other, then a voltage is developed or induced. So, this amount of voltage is produced depends on three things. First of all, speed through which we can move this these two things, that is magnet or this wire, that is one of the major important. So, the high speed produces the high voltage. Second is the magnetism. So, strong magnets produce high voltage, and third is shape of the wire. That means, you can see as we are increasing the number of coils in the wire, that will produce increasingly higher voltage. So, you can see here there are two things here, one is electrical field. So, electrical conducting wire here, and there is a magnet. So, if we move the magnet through this coil, there will be a current generation or voltage generation. So, this production of this voltage is depends on the speed through which we move this magnet. Secondly, the stronger is the magnet, produce strong voltage, and thirdly, if we increase the number of coil, then we can get the more higher voltage. So, how we use this principle in actual measurement of soil concentration? So, let us see this. So, basically these EM sensor or electromagnetic induction method is basically utilized in this EM sensor for soil science. So, this electromagnetic induction method is based on the measurement of the change of mutual impedance between a pair of coil or above the on or above the earth surface. So, basically through this instrument, this you can see here, this is a electromagnetic induction instrument. So, through this instrument we can measure the change of mutual impedance between a pair of coils. So, there are a pair of coil. So, you can see here there is one pair, and this is a pair of coil, this is the first coil and this is the second coil. So, the first coil is known as the transmitting coil and the second coil is known as the receiver coil, and they are separated by a fixed distance. So, in this electromagnetic or EM sensor, there are two coils which are separated by a fixed distance, one is transmitting coil and another is receiver coil. So, basically we measure the electromagnetic, we apply this EM method by measuring the change of impedance between a pair of coil or on or above the earth surface. How? We will see. And most of the EM instruments are comprised of two or more sets of coil, we can see here. Now, these coils are electrically connected. So, these two coils are electrically connected. So, these two coils are basically electrically connected, as you can see, and they are separated by a fixed distance. Now, this transmitter coil basically is used to generate a electromagnetic field at a specific frequency. So, basically it first generates a current, we will call it C1, and this current C1 induces a magnetic field. Why it induces a magnetic field? But because remember, earth acts as a big magnet. So, when we move these coils with respect to the earth's magnet, obviously there will be a electromagnetic induction. So, this transmitter coil produces a current 1, this current 1 induces a magnetic field M1, and this M1 induces C2 in the, so C2 is basically a a secondary current. So, this M1 induces a C2 in the subsurface and or on object of the surface. So, C2 further induces a second magnetic field, that is called M2, and M2 further induces C3 in the receiver. So, you can see here this first coil, a transmitter coil, produces a current C1 which induces a magnetic field M1. This magnetic field basically induces a current called eddy current, which is denoted by C2 in the subsurface, and then C2 induces M2 in the vicinity of the receiver coil, and this M2 or secondary magnetic field produces another current, that is C3 in the receiver. So, this is how this total flow of this electromagnetic induction goes on. Now, remember that the transmitter coil, basically, as I have told you, the transmitter coil is used to generate an electromagnetic field at a specific frequency, and this is known as the primary field. So, you can see here this is the primary field. So, the primary field causes electrical current to flow in conductive material. So, earth is a conductive material, so flow in the conductive material in the subsurface. The flow of the current in the subsurface, we know, and this is called the eddy current, generates a secondary magnetic field M2, which we have already discussed, and which is sensed by the receiver coil at the end. Now, remember that the magnitude of the secondary field sensed by this receiver depends upon the type of distribution of conductive material in the subsurface. So, in the earth, what are those conducting materials? The salts are the conducting materials, because they are basically dissociated in the ions. So, these ions are the conducting materials. So, this flow of current is basically mediated by the ions of the salts which are present in the subsurface. So, depending on the concentration of the salts, depending on the composition of the salts, the magnitude of the secondary field sensed by the receiver varies, and the so both induced and secondary field along with the primary field are detected at the receiver coil, receiver coil. So, this is how, when you move this EM instrument with respect to the soil surface, this primary this coil 1 or transmitter coil basically induces a electromagnetic, basically creates an electromagnetic induction, and this electromagnetic induction is helping a flow of current through the through the salt solution, through the salt ions, which are basically conducting materials, and this this current produces the secondary magnetic field, which is basically sensed by the receiver coil, and this is how, depending on the concentration and depending on the composition, we can see the variation of the salt concentration. So, this is how this electromagnetic induction method is basically works in the soil science discipline. Now, let me show you a picture. So, basically you can see 2 points. One is the electromagnetic induction, which is inducing voltage by changing the magnetic field around a conductor, and secondly, the important thing is any change in the magnetic field will induce a voltage. So, if we move this these EM sensor with respect to the earth's magnetic field, that will induce a voltage, which will be measured at the receiver coil. So, this is how we measure the salt concentration in the soil, and this is actually the instruments you can see. Basically, the researcher or the scientist has to move this bar, you can see it bar. So, there are two sensors at the two ends, two coils at two ends, and you can see when it moves with respect to the earth surface, then there will be creation of or induction of voltage. So, this is how this electromagnetic induction is basically measured in the soil. So, we have completed the soil. The next, let us talk about the analytical methods for trace elements. Now, the trace elements in the soil are frequently analyzed are cadmium, chromium, lead, copper, nickel and manganese. Apart from that, there are some metalloids also. Most importantly, arsenic is also measured by different methods, and there are certain methods which can measure most of the elements in the earth crust. So, depending on the type of analysis, there are different types of naming. For For example, the total analysis. The total analysis is basically the baseline analysis and it is essential for all the pollutant elements. So, essential and pollutant elements for we need the total analysis. For example, if we are interested to measure the lead concentration or lead contamination in the soil, we should go with the total elemental analysis, and total elemental analysis can also be done by different ways. So, total elemental analysis, for that you need to use certain kind of digester material, digestion mixture, for example hydrofluoric acid. And apart from this total analysis, you can go with the pseudo total analysis also. So, pseudo total analysis helps for the heavy metal and other pollutant contents also sometimes. Then there is an extractable elements also, which are basically mobile and plant available contents, which basically denotes mobile and plant available contents, and speciation also, which element form, phase, compounds, oxidation state. So, you can see depending on whichever form you want, you can use different types of reagents to extract that form. For total analysis, you have to use different extractant. For pseudo total analysis, you have to use different types of extractant. For extractable or mobile, you have to use different types of extractant, and so on and so forth. So, this is how, based on our desired output or based on our specific element, we go with the specific type of analysis. Now, there is no scope to discuss about different types of extracting reagents for each of these elements. However, I am going to talk about the important analytical techniques or analytical methods which we use for measurement of these trace elements. So, or different other elements also. So, let us talk about the atomic absorption spectroscopy. Now, we have already started talking about the atomic spectroscopy. Remember, we have already talked about the ICP-AES. So, it is one kind of atomic spectroscopy. Now, this ICP-AES, basically atomic emission spectroscopy. Now, we are going to talk about the atomic absorption spectroscopy. Sometimes it calls it is generally denoted as AAS or AAS. Now, this atomic absorption or AA is based on the principle that a ground state atom is capable of absorbing light of the same characteristic wavelength as it would emit if excited to a higher energy level. So, you can see here that a ground state atom is capable of absorbing light of the same characteristic wavelength as it would emit if excited to a higher energy level. So, every element for movement from the atom of every element, when it moves from ground state to the excited state, it basically absorbs a characteristic wavelength of radiation. Now, in flame atomic absorption, this is a type of atomic absorption we will discuss later. Now, in flame atomic absorption, a cloud of ground state atom is formed by aspirating a solution of the sample into a flame. So, that is why it is called flame atomic absorption. So, basically a cloud of ground state atoms is formed by aspirating a solution of the sample into a flame of a temperature sufficient to convert the element to its atomic state. So, basically this atomic absorption spectrometer basically allows the atoms to from this ground state to absorb certain wavelengths of wavelengths of radiation to go to their excited state. Now, remember that the degree of absorption of characteristic radiation produced by a suitable source will be proportional to the population of ground state atoms in the flame and hence to the concentration of the elements in the analyte. So, more concentration of the elements in this ground state or more concentration of the atoms of a particular element in the ground state, it will absorb more radiation, characteristic radiation. So, by this correlation we measure the concentration of a particular element through atomic absorption spectroscopy. You can see here this is an atomic absorption spectrometer and there are different types of attachment with it. We can attach the auto sampler for automatic sampling, we can attach the hydrate generation to enable it for for measurement of arsenic and other elements, specific metalloids. So, this is a basic form of atomic absorption spectrometer. Now, let us move ahead and see the principle. So, you can see that atomic absorption spectroscopy, we are introducing a compound and we are giving it, we are basically giving it thermal energy by producing heat, and then we are atomizing this compound. Now, this heat we can give either through flame or through graphite furnace. Now, when we basically produce the heat and produce the atoms, it absorbs certain radiation, certain wavelengths of radiation. Now, we can capture that, and the spectra of these atoms basically consist of the sharp lines. As you can see here, this is all these sharp lines which are generated from the spectra of atoms. Now, each element has a characteristic spectrum, and due to sharpness of the lines, there is a little overlap between the spectral lines. So, the spectral lines are very narrow and sharp. So, as a result of that, there is a very little overlap between the spectral lines of different elements. So, therefore, there is a very little interface. So, that is why this instrument is more or less interference free. Now, we know that when we are introducing the sample and producing the high temperature by either through flame or through graphite furnace, we are producing vapors, and it basically measures, and we are basically measuring the absorbance or emission of the atomic vapor. Now, in case of AS, we are basically measuring the absorbance, we are not measuring the emission. For emission, we are using the atomic emission spectroscopy. Now, atomic spectroscopy deals with both absorbance and emission. However, in case of AS, we are specifically concerned about the absorption. So, it deals with the atoms, so we cannot distinguish Fe2 plus from Fe3 plus. So, this is basically the principle of atomic absorption spectroscopy. Now, regarding the sensitivity of the atomic absorption spectroscopy, remember that atomic spectroscopy is very sensitive. It is a kind of atomic spectroscopy, right. So, this atomic spectroscopy is very sensitive for most of the elements, and concentration at the ppm level may be routinely determined using flame atomization, and we call it FAAS, flame atomic absorption spectroscopy, or another way is using electrothermal atomization, concentration at the ppb level. So, whenever, depending on the accuracy we want, depending on the level of detection we want. So, if we are interested in the ppm level, then a flame atomic absorption spectroscopy is okay. However, if you want to go with at the ppb level, then you have to go with the electrothermal atomization, which is being given by graphite furnace. Now, that is why this instrument is known as GFAAS, or graphite furnace atomic absorption spectroscopy. Okay. Now, this is the principle of absorbance, you know all this. So, absorbance is minus log by IT by I0, where IT is the transmitted radiation and I0 is the incident radiation on the samples. So, this is how these atomic absorption spectroscopy basically works. So, this slide basically shows the schematic diagram of atomic absorption spectrometer. So, basically this is how it works. So, basically first of all we introduce the sample in the nebulizer, and we are injecting an oxidant which is generally air, and then this sample with the oxidant moves to the cloud chamber, and in the cloud chamber we introduce a fuel. Generally this is acetylene, sometime other gases are also used, like hydrogen is also used. So, in the fuel chamber, in the cloud chamber, it will make a cloud of atoms, and this cloud of atoms basically goes to the burner, and in the burner, in the contact of the flame, so atoms will be in contact with the flame, and when they are contact in the flame, they will absorb certain radiation. Now, this radiation, characteristic radiation, has to be produced from some source. So, this source is basically this HCl or hollow cathode lamp, and this hollow cathode lamp will produce a characteristic very narrow radiation or almost monochromatic radiation or wavelength, which is basically being absorbed by this particular element which we are interested in, and as a result of that, after it absorbs the radiation, then we can get the transmitted radiation, and then of it moves to a monochromator, to a detector, and then amplifier, and ultimately to the output. So, from there we can get a spectral lines and have an idea, okay, these are the wavelengths which they have absorbed, and from there we can get the concentration of that particular element. Remember that this hollow cathode lamp is very specific to a specific element, and this hollow cathode lamp generally utilize a specific monochromatic radiation which is being absorbed by that particular element in which we are interested in. So, this is how this analytic A spectrometer basically works. So, friends, let us wrap up here, and in the next lecture we are going to talk about more about the hollow cathode lamp, and then we will talk about other methods of inorganic pollutants, and then we will be talking about the organic pollutants measurement method. Let us wrap up this. Thank you very much.